last lecture I talked about the stability of the solar system. Now we have, of course, thousands of exoplanets, and we'd like to generalize what we've learned about long-term stability of the solar system, understanding long-term stability of other planetary systems. And so the question that you would like to be able to answer is, suppose you have n planets with masses m sub I, 7 major axes, a sub I, let's say nearly circular, nearly coplanar orbits. And the question is it stable for 10 to 10 years? We know the answer for the solar system. As I described yesterday, it has a sort of 99% chance of being stable. It's chaotic, and therefore the future evolution is not predictable, but if you do an ensemble of nearby solar systems, you find that in about 1% of some catastrophic event, usually involving Mercury. So the question is, can we generalize this to other systems? And the signs are not good, because first we saw that the system's chaotic on very short time scales, a few million years, but that doesn't tell you whether it's stable or not. Second, we found that the answer was strongly dependent on small changes in the initial conditions, on minor effects like general relativity and so forth and so on. So this is obviously a hard problem. It's an unsolved one, but you might hope that you could find some empirical ideas about what's happening. And in order to introduce get us up to speed on the knowledge that we do have, I just want to make sure that we have a clear definition of the idea of the Hill radius. So let's imagine that you've got two planets, or better yet, a planet and a test particle. So the star mass m is way down here at some radius r. You've got one planet here with mass m, and you've got a second test particle with a semi-major axis that's different by some small amount x. And I'm going to go into a rotating frame. We'll assume this is on a circular orbit so that it's fixed into a frame that's rotating with its angular speed, which is n r square root gm over r cubed. So in that frame, this test particle is going past at a velocity v. The mass m is rotating this way, so this is further out. It's got a lower angular speed, so it appears to be going backwards. And the velocity, because it's in a rotating frame, is r plus x times the angular speed for something at r plus x minus the angular speed mass of the bigger mass in r. You expand that for x much less than r, and you get minus 3/2 n over r times x, just due to the shear, the Keplerian shear. So we can ask, how big a perturbation does this get as it goes past the mass m? I'm going to do this very approximately. Approximately, as it goes by, it feels a force which is roughly gm over x squared. The force lasts for a time interval, which is roughly the time it takes to go past, which is roughly x over the velocity. And so the change in velocity that it gets is delta v roughly f delta t, which is gm over xv. And This is very crude. It's neglecting Coriolis force. It's neglecting the details of the change in force as it goes past. But I'm just trying to make an approximate argument. And the perturbation that it gets is strong, obviously, if delta V is of order V, and that in turn says that it's strong if X is greater than approximately GM over V squared. But we know that the velocity depends on X, not worrying about the factor of 3/2. This is approximately GM over N squared X squared, so the perturbation is strong if X cubed is, if X is less than. If X cubed is less than approximately GM over N squared, we know what N is, and so this is roughly R cubed times the ratio of the mass of the perturber to the mass of the central star. And that leads us to define a characteristic radius called the Hill radius, which is the radius of the perturber times the mass relative to the mass of the star, with a historical factor of 3 in there. This, you've already seen this. Douglas introduced it as the tidal radius. The physical reasons why it's important for tidal limitation of the globular cluster is quite different from the reasons why it's important in a planetary system. And so part of the thing to keep clear is that this has a large number of names depending on what context it's in. So I think you called it the tidal radius?
Probably.
Okay. So it could be called the tidal radius. It's sometimes called the Lagrange radius because it's the distance to the collinear Lagrange points for a small body orbiting a large one. It's sometimes called the Roche radius because it's closely related. Lagrange radius. Roche radius, it's sometimes called the Hill radius, and it's sometimes called the limiting radius.
Jacobi.
And sometimes called the Jacobi radius. So all of these are the same. I can't help it. The factor 3 is in there so that it coincides with the precise definition here. Some people leave out the factor of 3 when they define it. So that's all I can say. It's important to generalize this a little bit because in a planetary system, you don't have a test particle plus a single mass. And the way it's generalized is to define what's called the mutual Hill radius. Between two planets, which says that RH is the average of the orbital radii of the two planets, the sum of the masses, 3m, 1/3. You might say this is totally arbitrary, but in fact it's not. The case you're interested in, the masses are relatively small, so the interaction between them is only important if the radii are pretty similar. So almost any natural definition of the mean radius would give the same result here.
I think the tidal radius is measured from primary. Co-op reading that it's measured from the same.
No, the tidal radius is measured from the secondary too, at least for something like a small cluster orbiting in a large galaxy. You might also argue that this is arbitrary, that you could do m1 to the 1/3 plus m2 to the 1/3, but in fact, if you look at the dynamics precisely in the limiting case where you have two small bodies that are close, there's an analog to the decomposition that you see in the standard Kepler problem, that says that the dynamics only depends on the relative position and the sum of the masses. So this is really pretty much a unique definition. Okay. In the limiting case where you have two bodies on nearby orbits, they're on circular coplanar orbits, the masses are small, that is M1, M2, are much less than the mass of the host star, then those two bodies are stable if absolute value of the difference between the radii is bigger than 3.46 times the neutral Hill radius. This is a result that has been around for a while. The standard reference for it is a paper in Icarus by Gladman, 1993. It's a rigorous result, and you can prove it analytically, and moreover, that it's a result that holds for all time. That is, if this criterion is not satisfied numerically, the system will disintegrate or change drastically on a rather short time scale. If it is satisfied, you can follow it for as long as you want, and it will always be stable. That's the criterion for a system with n equals 2. If you go to larger n, what you find is that first, there's no analytic stability criterion. Second, that in general, the system, you don't have the characteristic that the system is immediately unstable or always stable. That is, what will typically happen is that it may be stable for thousands, millions, huge number of orbits, and then become unstable. And so what you find is that it's stable for, let me call it, stable for a time t if the separation, all the separations, absolute value of Ri minus Ri plus 1 for adjacent planets is bigger than some dimensionless number time over the orbital period times the neutral Hill radius. That is, the separation in terms of number of Hill radii has to be bigger and bigger as you follow it for a longer and longer time. And for, this is the orbital period, we're interested in typical values of T over P, number of orbits about 10 to the 10th. And the numerical simulations suggest that K at 10 to the 10th is roughly 10. You heard about this already from Yen Chin. This is there's a variety of numerical experiments that indicate this. Yen Chin, is your stuff published yet?
But other people are published.
Sorry?
This kind of numerical experiment has been published by other people.
Yeah, so there was a paper by, the one I usually use is a paper by Smith and Lissauer, 2009. These numbers, they vary a little bit, maybe from 9 to 12, but roughly all the experiments are consistent.
Can I just add a comment? I think this K function is actually probably depends on mass. It probably depends on your number of planets.
Yes, so the calculations are limited. For example, Most people use a set of equally spaced planets that are all the same mass for simplicity. It's obviously approximate. You're right that it depends on mass. That is, it's not even obvious that it should scale like the 1/3 power of the mass. There are arguments for other powers, but the other powers are kind of close, and for typical planetary masses, it doesn't make a whole lot of difference.
Time dependence is linear.
Sorry?
Time dependence is linear?
No, the time dependence, I mean, this time dependence? No, it's probably exponential, it's probably logarithmic, or I think there's even a claim that it's the log of the log. All you do is you run it for a bunch of times and see the results. If you wanted 10 to the 12th, this would probably, increase by 10 to 20%. And that's about it. Now, the thing that's most impressive is you now know as much as anybody does about the answer to this problem. All we have is this exact result, this empirical result. So if somebody gives you a new exoplanet system and says, is it stable? If it's got more than 2 planets, you've got 2 choices. You apply this criterion, or you stick it in the computer and do an n-body integration. You don't know anything more than that. So the situation, I would say, is not good.
The period, when you have several objects, which period do you?
Well,
the smallest
you
one?
do this for each adjacent pair of planets.
And from the two, they're not going to be too different, so.
Yeah, there'll be slightly different periods, but trust me, if this is 10 and 10 to the 10th, whether it's 1 times 10 to the 10th or 2 times 10 to the 10th.
Oh, no, so T is 10 to the 10th.
Yeah, so it's not going to make much difference.
What about non-circular orbits?
Well, they're probably less stable.
No, but let's say, can you find for n equal 2, let's say non-crossing orbits, can you find an analytical?
I don't think
Clemens result is general for any sensitivity.
which one?
Clemens result.
Well, it depends on how you define R1 and R2. I think it's correct that Gladman's result doesn't require the orbits are circular, but I'm not sure how it's modified in the case. You can write, that's right, you can write down a more general formula. It's a complicated function of the eccentricities for 2 planets. For multiple planets, what you basically do is you say, well, instead of the difference in semi-major axes, take the difference between the pericenter of the outer one and the apicenter of the inch, and is shaken.
It's much steeper than that.
Okay.
Do you gain in stability if they're mutually inclined?
It is a reasonable assumption that since they're mutually inclined, the distances are bigger, and that makes it more stable, and if they're eccentric, the distances are smaller, and so they're less stable.
Citation, secular.
Second is much stronger.
Once the inclinations are big, all bets are off.
Has anyone actually found this which is smaller than
Yeah, I think some of the numerical simulations put in small inclinations. Obviously there's a huge number of experiments you can do, but all of these results, once you go to more than 2 planets, are just empirical. Okay, so having disposed of this problem, I'll go on to the next topic. What I'd like to do at this point is to give some basic results in analytic perturbation theory for planetary systems. So the general problem is something we've seen already. You have a planet that has a Kepler Hamiltonian, so it's p² minus gn over q, and there's some additional potential phi, which depends on q in time. The assumption is that, and you of course write this as a Kepler potential plus perturbing potential. The assumption is that the perturbing potential is small. and you'd like to know what its effect on the Kepler orbit is. This is done by perturbation theory. In fact, this is the problem for which perturbation theory was invented. If we were living in the 18th or 19th century, most of physics and astronomy was solving this problem. And all the people who are working on string theory now would have been working on this problem back then. A lot of this is very similar to the stuff that Dave Merritt talked about a couple of days ago, or I guess yesterday. One of the differences is that we're using completely different notation, so just let me remind you of the notation. I'm going to be doing a lot of this in Delaunay elements. So Delaunay actions are g times the mass times the semi-major axis, GMA 1 minus d squared, and square root of GMA 1 minus d squared cos the inclination. And my notation, which follows Delaunay's, this is L, G, and H, and Dave's notation is that this was I, this was L, and this was LT, because this is the angular momentum, and this is the z component of the angular momentum. I would say that Dave's notation is more rational, but mine has historical precedent and is more commonly used with planets, so you're more likely to see it. The corresponding angles in my notation were the mean anomaly, the argument of perihelion, and the longitude of the nodes, and Dave called this M for mean anomaly, but remarkably used the same notation that I did. And the right way to think about how to solve this problem is that there are two components of trying to solve any problem in perturbation theory and celestial mechanics. One is to solve Poisson's equation, to figure out what the perturbing potential is from the mass distribution. And the second is to solve the dynamics. So the other way to look at it is that you've got Newton's law of gravity, and Newton's laws of motion. And you have to pick some set of coordinates to solve these. And there are two natural coordinates. There's, of course, Cartesian coordinates, and there's action angle variables, or if you like, Delaunay elements. If you want to solve Poisson's equation, that is, if you want to find the potential that arises from a mass distribution, you clearly want to use Cartesian coordinates, because it's relatively easy in Cartesian coordinates, and really hard in Delaunay coordinates. If you want to solve the laws of motion, that's using perturbation theory, that's really hard in Cartesian coordinates, and relatively easy in Delaunay coordinates. And so the question is which you're going to do, and the almost universal experience is that solving these is a lot harder than solving this. So you should use Delaunay coordinates and just swallow the fact that the potential theory is going to be difficult. Because it's a lot easier to do the potential theory than the dynamics. So how do you proceed? This is a Hamiltonian. So you can write, you can use any set of canonical coordinates, and the equations of motion will look the same. We're going to use the 1A coordinates, and so the Hamiltonian, Kepler Hamiltonian is just minus GM squared over 2L squared, and then there's a perturbing Hamiltonian, which is a function of all three momenta and all three coordinates. So you can immediately see why the potential theory is more complicated. You've gone from a potential that only depends on three coordinates to all three coordinates and all three momenta. But there are things you can do to get a little better handle on what the perturbing Hamiltonian looks like. The first is to recognize that all of these coordinates are angles. That means that the position, if you change the anomaly by 2 pi or either of the other coordinates by 2 pi, you end up in exactly the same position. That means that the perturbing Hamiltonian is periodic in all three angles, and so you must be able to write it as a Fourier series, which depends on three integer coordinates. There's some coefficient in front, which depends on I, J, and M, and three momenta, and then is multiplied by a cosine of I times the mean anomaly plus J times the argument of periapsis plus M times the node plus some phase, which I'll call phi IJM, which might also depend on the time. Okay, so it's always got to be a Fourier series. I can write that maybe more usefully in terms of mean longitude, which is L plus omega plus capital omega, and the longitude of periapsis, which remember is little omega plus big omega, and this becomes I times lambda plus J minus I times omega plus M minus J times omega phi IJM. So the next thing to notice is that suppose the orbit is circular, the orbit of the object that you're trying to follow. Well, if it's circular, the longitude of periapsis is not defined because you don't know if it's circular, so there's no periapsis. So the Hamiltonian can't depend on this. So J has to equal I. Similarly, if the orbit has no inclination, even if it's eccentric, the node isn't defined. So it can't depend on this coefficient. So M minus J has to equal to 0. And that leads to a general criterion that the function out in front depends on the actions, has to go as a function of L minus G, which because these differ by square root 1 minus E squared, this is 0 if the orbit's circular. It turns out this is to the absolute value of J minus I over 2. Similarly, depends on G minus H, the absolute value of M minus J over 2. That is, the orbit's circular, L is equal to G. If it's not circular, which is okay. The orbit's circular, L is equal to G. It says that this factor is 0 unless the exponent is 0. And this general property was first figured out by D'Alembert. It's now called the D'Alembert characteristic. And there's nothing really magic about this. The simplest way to think about it is suppose you have some smooth function in ordinary Cartesian coordinates of x and y, and you try to expand it in polar coordinates around 0. It's going to be some constant plus f1 r times the cosine of phi minus phi1 plus f2 r squared times the cosine of 2 phi minus phi 2 and so forth. That is, all that this says is that you've got to you have a smooth potential, and you're trying to expand it in this particular set of coordinates, this is a necessary way to avoid singularities in the coordinates at the middle. You can do a little more in the one of the obvious cases is in, say, a two-planet system. You're trying to follow the motion of one planet due to perturbations from some other planet outside. In that case, the perturbing potential would be some function of the cylindrical coordinates where the azimuthal angle is phi minus the phi of some satellite. You would expand that in the Fourier series phi m r and z cos m phi minus phi s. Well, if that were true, suppose you just rotate the zero of the coordinate system a little bit. If you just rotate the zero of the coordinate systems, and you look here, it doesn't affect the mean anomaly, it doesn't affect the argument of perihelion. It increases the node by m times the angular change in the coordinates. In this case, if you rotate the coordinates, the same thing happens. And so this m has to be the same as this m. And what I've called phi ijm has to be minus m phi s. That is, the integer that I've called m here is the same as the azimuthal wave number for Fourier expansion of the potential. Okay, so that's about all you can do generally. What I'd like to do in the rest of the time is give 2 or 3 specific examples of, I think, interesting and useful problems where you can actually work out, use this formalism to work out the behavior of a satellite or a planet. And what I'd like to get out of this, in addition to some feeling for the results in these particular examples, is to recognize that this procedure, can be relatively straightforward. First, second, that it gives you results that are really hard to derive any other way. And thirdly, by doing these examples, persuade you that all that stuff you took about Hamiltonian mechanics when you were undergraduate wasn't just an introduction to the Schrödinger equation or pointless torture, that it really does have practical uses that make it a very powerful tool. I should say that many years ago I had the privilege to know Vicky Weisskopf, who was one of the great physicists of the last century, and he had a standing claim that any problem somebody could solve with Hamiltonian dynamics, he could solve without it. And unfortunately, at the time, I didn't try to challenge him on any of these, but although I have enormous respect for him, I think that that was a wrong-headed way to look at it. Okay, the first sample problem I'd like to describe, and maybe the simplest, is the motion of a satellite around a planet like the Earth. The thing that makes this complicated is that the Earth is not a perfect sphere, although I'm going to assume that it's axisymmetric. So motion of the satellite around an axisymmetric planet. If the planet's axisymmetric, its external potential is conventionally written as minus gm over r, 1 minus sum over n, Jn r to the n, r to the n, Pn cos theta. So r is the radius of the planet. And Pn is a Legendre polynomial. And Jn is the multiple moment. This has, the only physics in this equation is that outside the planet there's no mass, so you need a potential that's a solution to Laplace's equation. The other thing to notice here is that this sum starts at n equals 2. J1 is always 0 if the origin is the center of mass of the planet, which is the natural thing to assume. For most planets, including the Earth, if they're rotating, there's an equatorial bulge, and rotation means that J2 is much larger than any of the other coefficients, and so I'm just going to write the potential, including only J2. And I'll put in the Pn of cos theta, so it's 1 minus J2 r squared over r squared times 3/2 cos squared theta minus 1/2. The other thing to keep in mind is that it doesn't really matter what you pick for the radius of the planet. The only thing you have to make sure is that the value for the multiple moment that you're using is for the same definition of the radius of the planet. That is, all that matters is the product of the two. The radius and J2 only enter in this product. Okay. Well, this kind of problem was already addressed by
Theta is the angle.
sorry, theta is the polar angle from the symmetry axis of the planet. Right, so theta is pi over 2 in the equator. This is very similar to one of the problems that Dave talked about. I think his, I forget exactly the correct analogy, but Dave argued that the biggest effects in his case were likely to be from the components of the potential that you got from averaging over the orbit. That is, that there will be short period oscillations in the orbit of the satellite as it goes around the planet, but the ones that are likely to have the biggest long-term effect are the ones that remain after you average over one orbit, and that it's easier to average the potential over the orbit rather than working it out in detail and then doing an average after you've worked out the dynamics. So the next step is to orbit average. Notice that in this way of looking at things, an orbit average is exactly the same as keeping only the terms of I equals 0. Well, some of these averages we've worked out before. So to work it out, in that case, you'll need an orbit average of 1 over r and 1 over r cubed and cos squared theta over r cubed. I'm not going to try to work those out. They should be straightforward to work out using standard properties of Kepler orbits. I'll just give you the answer. It's that H1 or phi is Gm fourth J2 r squared over 4 times 2 of the Delaunay elements, G cubed, 1 minus 3 h squared. G squared. So this is the perturbed part, the potential, and of course, the Kepler part is minus Gm squared.
So it's like you're using two G's, so the GM is the
Yes,
gravitational
yes,
constant and then the
yes.
other G is the action?
Yes, yes, so that G is the gravitational constant, this G is the action. I can't help it. But as you saw, it's obvious which one's which. So having done this, look at Hamilton's equation. What do you learn? Well, the H1 with respect to the mean anomaly doesn't appear in here, it's 0. So that says that L is constant. So it says the semi-major axis is constant. The argument of perihelion doesn't appear here either. So that says that G, which is L squared root 1 minus E squared, is constant. So we already know that this is constant, so the eccentricity must be constant. Similarly, H1 omega is constant, which says that the inclination is constant. Similarly, the rate of change of the argument of perihelion, omega dot, is dH by dg. Just do a derivative of this with respect to this g, but not that g, and I'll just convert it back into standard Kepler elements: 3 Gm to 1/2 J2R squared over 4 A 7/2 1 minus E squared squared 5 cos squared of the inclination minus 1. And a similar expression for the rate of precession of the node is minus 3 Gm to 1/2 J2R squared cos of the inclination over 2A to 7/2 1 minus E squared. Okay. This is the rate of precession of the eccentricity vector, or the apsidal direction of the satellite. You'll notice that for low inclination satellites, it precesses forward or prograde. For high inclination satellites, it goes backwards. There's a critical inclination, which is the arc cosine is 1 over square root of 5. With a satellite where the node doesn't precess at all, and I think this is actually used by designers of satellite orbits because it has some particular desirable property. And again, what I'd encourage you to do is to think about how you derive these results without using these tools. It's actually not very hard to derive this one and this one for circular orbits, but I wouldn't want to try to do it for eccentric orbits, and this gives the full eccentricity dependence immediately. I also want to point out that there is one curious and remarkable feature of this derivation, which is that you'll notice that the Hamiltonian is independent of the argument of perihelion and of the node. The independence of the node is obvious. It's just because we assume the Earth was axisymmetric, and then it can't depend on the Hamiltonian can't depend on the azimuthal action of the node. It's far from obvious why the orbit average potential shouldn't depend on the direction of the perigee. I think it might depend on whether it was pointing to the equator or pointing to the pole. Moreover, what's even more worrying is that if it did depend on the argument of perigee, then this partial derivative wouldn't be zero, and the angular momentum wouldn't be constant, and the eccentricity wouldn't be constant. Well, what that says is that if you have a satellite that's orbiting, just above the 100 kilometers above the atmosphere, if the eccentricity changes even a little bit, the perigee will change a little bit. It'll start to plow through the atmosphere, and it'll crash. So the answer to all this is that this derivation is correct. The answer doesn't depend on the perigee. This is an accidental consequence of the particular properties of these averages and particular properties of the quadrupole potential. But that if that accident wasn't there, you would actually have a lot harder time keeping satellites from crashing. I'm sorry? Well, no, if you include J4, the Hamiltonian does depend on the argument of perigee. So it's an accident that only applies to J2. Okay. So this is one example of what you can do. The second example is what's sometimes called cosine oscillations, but what I call leadoff cosine oscillations, because I think leadoff is the one who deserves the credit. And this is going to be a very similar derivation. The difference is that the perturbing potential is going to come not from the shape of the Earth, but from a distant companion. So I'll assume there's a companion which has some mass, m sub c, and some position, x sub c, in coordinates centered on the star, that is something like heliocentric coordinates. The perturbing potential is the direct potential plus the indirect potential, which we derived the last time. I'm assuming it's a distant companion, so x is much less than xc. That means I can expand this as 1 over x minus xc, 1 over xc, 1 minus 2x dotted with xc squared, x squared, xc squared, to minus a half. Again, because we're talking about a large xc, you can simply do a Taylor expansion of that. You get 1 over xc, 1 plus x dot xc over xc squared, means x squared, 2xc squared plus 3 halves dot product squared over xc before, plus a set of terms that I'll neglect. Okay, so, and then I'll substitute this in here. The first thing you notice is that this term depends on the companion, but all we're interested in is the dynamics described by the position x. So this doesn't depend on the orbital elements. It has no effect. It has just a constant term in the potential. There's no effect on what's going on, so I'll take that out. The second thing to notice is that this term, the one that's linear in position, cancels the indirect potential. So I can take that out and that out. And what I'm left with is a perturbing potential that's g times the mass of the companion, or the distance to the companion, q times a half x squared minus 3 halves x, with xc squared over xc squared. And this, of course, is called the quadruple potential. It's different from the potential arising from the quadrupole moment of the Earth, because this is an external quadrupole and the other is an internal quadrupole. Okay, just as in the case of a satellite, the next thing to do is to orbit average. We even have the words right here. In this case, however, we've got two bodies. We've got the satellite, the object that we're interested in at small radii, and the perturbing object at large radii, and we want to orbit average over both of them. That means that the orbit average is a little more complicated because of this dot product. I'm not going to go through the algebra. I'm just going to give you the result. I'll convert this. I'll start calling this H, since I'm going to be doing it in orbital elements. After the two averages, GMC, square of the semi-major axis, companion eccentricity, the 3 halves, 1 minus 6 e squared minus 3, 1 minus e squared, cos squared, inclination, plus 15 e squared, sine squared the inclination, sine squared the argument period. Now, at this point, what I should do is convert this into Delaunay elements. That's extremely easy to do, but I'm not going to bother, because most of what we're interested in you can get from this already. First thing to notice is that this is independent of the longitude of the node. That is, pH by the omega is 0. That says that the Delaunay element H is conserved, and that in turn says that 1 minus e squared cos squared I is constant. Because the orbit average, it's independent of mean anomaly, and that says the semi-major axis is constant. In contrast to the case with the Earth's quadrupole moment, this does depend on the argument of periapsis. I should also say that the fact that this is axisymmetric, that is, that it's independent of the longitude of node, is not obvious in contrast to the case of the Earth. There, it was necessary because the Earth was assumed to be axisymmetric. Here, the outer satellite orbit can have some eccentricity, so it's not axisymmetric. But again, this is an accidental feature of the quadrupole potential that at this order it does turn out to be axisymmetric. If you included higher orders, you would lose the axisymmetry. You would get more complicated behavior on which a number of people here have worked. Okay, well, having gotten this far, if you look at this Hamiltonian, it doesn't depend on the longitude of the node. It doesn't depend on the mean anomaly. It doesn't depend on the semi-major axis. This is a constant. So the only variables that are left are the eccentricity and the argument periapsis. Moreover, the Hamiltonian has to be conserved. So that says that the whole motion is reduced to 1 degree of freedom, and you can figure out what's happening just by plotting level surfaces, the Hamiltonian on the plane of the eccentricity, the argument of perihelion. And the way to see what's going to happen is, let's imagine that we have a star, we have a planet orbiting it on a circular orbit. We want to know how the orbit is affected by this external potential. I'm going to assume that the orbit is initially circular with some initial inclination, so I can replace this constant by cos squared of I0. And to see what's going to happen, I just have to demand this quantity stays constant. So that quantity is 1 minus 6e squared. 1 minus e squared cos squared I, we know is a constant. So we have minus 3 cos squared I0 plus 15 e squared sine squared omega. And I'll eliminate sine squared I as 1 minus cos squared I. And I get 1 minus cos squared I0 minus e squared. That has to be a constant, so it has to be equal to the initial value. Initially, the eccentricity was 0, so you have a 1. You have minus 3 cos squared I0. Initial eccentricity is 0, so this term goes away. So that cancels that. This cancels this. You're left with two terms. Both are proportional to e squared. So there are two possibilities. Either e squared is 0, or, let's see, there's a common factor of 3 here. So minus 2 plus 5 sine squared omega, 1 minus cos squared I0, and 1 minus e squared is 0. Okay, I can rewrite this as multiplying through 2e squared minus 2 plus 5 sine squared omega sine squared I0 minus e squared. Okay, well, when omega is 0, this is 2e squared minus 2, which is always negative, so there's no solution. So there can only be a solution to this if this changes sign between this being 0 and this being unity, and that tells you there's a solution if and only if sine I0 is greater than or equal to square root of 2/5, which corresponds to I0 39.2 degrees. Okay, what does this tell you? It says if the initial inclination between the planetary orbit and the orbit of the companion is less than 39 degrees, the only solution is e squared equals 0. The orbit started circular, it'll stay circular, nothing's going to happen. If you're above this critical inclination, there are possible solutions with non-zero eccentricity. This doesn't tell you exactly what's going to happen, but in fact it turns out that the circular orbits are unstable and will start to require an eccentricity. In fact, they will oscillate between circular and non-zero eccentricity. The maximum eccentricity is square root of 5 sine squared I 0 minus 2 over 3. And these are lead-off cosine oscillations. The reason that it's not clear exactly what happens here is because these are the wrong coordinates. It would really be better to do this in terms of Poincare variables, that is e cos omega and e sine omega, then it would be clear that excitation of the eccentricity was inevitable. The reason that these are so important is that You'll notice that this argument says nothing about the strength of the perturber. The strength of the perturber, the mass of the perturber, and the distance of the perturber only enter as a constant factor in the Hamiltonian. That means that all they affect is the time scale of the oscillation, not the amplitude of the oscillation. So it means that extremely small perturbations can create oscillations in the eccentricity of order unity. Well, you can ask, at what point does that become an absurd argument? As if the mass of the perturber is epsilon, are you still going to high eccentricity? The answer is sort of yes. That is, what stops the oscillations in the end is either that the age of the system is shorter than the oscillation period, in which case it just doesn't have time to get to high eccentricity, or there's some other perturbing potential, there's some other component of the Hamiltonian that makes the apsidal direction precess fast enough to kill off the effects of this Hamiltonian. In exoplanet systems, the two most important possibilities are other planets. If you have more than one planet in the system, you can suppress the lead-off Kozai oscillations. If there's no other planet and the planet's relatively close, it's suppressed by general relativistic precession. So one of the remarkable consequences of this is that you can't understand planet formation without including the effects of general relativity. And let me say again that this is somewhat oversimplified because it's only got a quadrupole moment because it's neglecting the angular momentum contained in the planet. A more precise description includes octopole and higher order terms, and in those cases you don't have this accidental symmetry, and behavior becomes more complicated. Now, I did have a couple of slides to show on this. So this is an example of the oscillation. Again, these are the level surfaces of the Hamiltonian. Circular orbits are down here, and at least in these coordinates, the orbit stays circular, the axis direction precesses, it reaches a separatrix here, and then goes up to high eccentricity, oscillates back down on the circular, and then continues on a circular orbit. Again, this is somewhat misleading because, of course, if you're circular, the periapsis is not well defined. This plot is more useful for describing what happens when you have a non-zero initial eccentricity. And in that case, you still get an oscillation. Another remarkable thing about this is that all of this could have been done by Laplace, right? Laplace understood all of these tools perfectly well, and as far as I can tell, they just didn't do it because they weren't interested in things with large inclinations and eccentricities. It was first discovered by Leadoff in 1961. He was interested in the effects of the moon on satellite orbits. At the conference where he presented the results, which was in the Soviet Union, I think Kozai was there, and Kozai later, within a year or so, started applying it to asteroid orbits. The second remarkable thing, of course, is that even though these results were published, they were basically ignored for an extended period. This is the ADS record, and you can see from 1960 up to the early 1990s, there were essentially zero citations to either of them, and since then the citations have been growing exponentially. Let me just say a little about some of the applications. One is to the irregular satellites of the giant planets. All of the giant planets have a large number of satellites in eccentric, inclined orbits. They are much smaller than the regular satellites, but they completely dominate the total numbers. The current numbers of satellites for the giant planets are 65, 62, 27, almost all of those are irregular ones. That's a picture of the regular satellite orbits. And the striking thing is that the inclinations of these orbits, this is for Jupiter, Saturn, and Uranus. The lengths of these indicate the range between pericenter and apocenter. They're inclined. There are some with prograde, some retrograde, and nothing at high inclinations. And it's almost certain that the reason there's nothing at high inclinations is that these limits are roughly the critical angle for Kozai oscillations. The ones above this have sufficiently large Kozai leadoff oscillations that they occasionally have pericenters where they interact with the inner satellites or fractions of the planet. Another natural question is whether these have something to do with the eccentricities of exoplanets, which we know are much higher than the solar system. This is a plot of the eccentricities and orbital periods of all the exoplanets. And so a natural theory might be, well, all the high eccentricity ones are in binary stars. These red dots are the exoplanets and binary stars. Clearly, this explanation doesn't work. There's no obvious segregation between the binaries and the singles, except for the fact that the 4 or 5 planets with the highest eccentricities here are all in binary stars. So maybe, leadoff Kozai oscillations in binary stars are the cause of some of the highest eccentricities. They're also relevant for formation of binary stars. Roughly 2/3 of stars in the solar neighborhood are binaries. A significant fraction of them are also triples. These are hierarchical triples in which there's a difference of several orders of magnitude between the semi-major axis of the inner binary and the outer component. In that case, you would normally expect the formation of the inner binary and the outer larger binary ought to be kind of independent events because the scales are different by orders of magnitude and they shouldn't have anything to do with each other. That's not true. This is the fraction of close binary systems that have an outer third body. And you can see that the fraction of binaries with periods of 20 days or longer is about 30–40%, but it rises to essentially unity at periods less than a few days. That is, all binaries with periods less than a few days have a triple companion. The obvious explanation is that the companion has introduced leadoff Kozai oscillations in a wider inner binary and made the periastron sufficiently small that tidal friction has circularized it into a much smaller binary. Blue stragglers, Haggai, knows much more about this than I do. These are objects that are found in clusters outside, beyond the turnoff point in the main sequence. So they're anomalously young because they should have evolved off the main sequence already. There's a variety of explanations for them, but Haggai has argued that they might be formed by leadoff Kozai oscillations in a triple system. Many of the hot Jupiters have remarkably high obliquities between the spin axis of the star and the orbital axis of the planet. Again, it's possible that those are generated by leadoff Kozai oscillations. I could go on, mergers of black holes and galactic nuclei, comets, artificial satellites, asteroids, type 1a supernovae, and so forth. All there's at least a possibility that leadoff Kozai oscillations have played a role in formation and evolution. Okay, the last topic I'd like to describe, or the last application of perturbation theory that I'd like to describe has to do with orbital resonances. This is a very rich subject which would require many lectures to cover, and I'm just going to try to give you a flavor of how you can use these tools to study them. Orbital resonances occur all over the place. There's Neptune and Pluto are in a 3-to-2 orbital resonances. Many of the objects in the Kuiper belt are in resonances with Neptune. There are the Kirkwood gaps in the asteroid belt. Many of the satellites around the giant planets are in orbital resonances. There are signs of orbital resonances in planetary rings. It appears that a significant fraction of the exoplanets are in orbital resonances. There are also spin-orbit resonances. Mercury's spin is 3/2 its orbital angular frequency, and so forth and so on. In order to understand the dynamics of resonances, you really have to use a Hamiltonian perturbation approach. So let me look at just one simple example. I have a exterior companion on a circular orbit. So it has a semi-major axis, A sub c, it has mass, M sub c, and it has a azimuthal angle phi sub c, and I'll just choose the origin so we can zero at time 0. In this case, I've already argued that in this Fourier expansion, phi ijm is minus m nc t. That is, the phase angle is given by the azimuthal wave number times the azimuthal position of the companion. We've also argued that the coefficients here, because of the D'Alembert condition, are proportional to L minus G, the absolute value of J minus I over 2, which is roughly the eccentricity of the absolute value of J minus I. Similarly, proportion to G minus H, the M minus J over 2, which is roughly the information the M minus J. Again, to keep things manageable, I'm going to assume that the planet we're interested in and the exterior companion are coplanar. That means that the inclination is 0. That means that the only terms here that are relevant are the terms J equal to M. I'm also going to restrict myself to the condition where the eccentricities are small. Since the eccentricities are small, the strongest term is going to have J equals I, and that in turn is equal to M. And so the argument of the strongest term in the cosine is going to be M times L plus omega, it's capital omega, minus M MC T. If I take a time derivative of that, it's clear that this argument of the coefficient is going to vary slowly, and we're going to have a resonance if and only if n is equal to nc. That is, if the mean motion of the planet we're interested in is the same as the mean motion of the companion. That does sometimes happen. For example, it happens in the Saturnian satellites Janus and Epimetheus, but it doesn't typically happen in planetary systems because if the mean motions are the same, the orbits are typically the same and they're going to collide. So I'm not going to consider these terms, which are typically called co-rotation or one-to-one resonance. I'm not going to consider these any further. The more general and interesting resonances are when the two planets are in different semi-major axes. And again, looking at these, the if you can't have the terms with zero exponent for the eccentricity, look at the ones with an exponent of 1 for the eccentricity. So look at the ones where j minus I is plus or minus 1. That says that I is equal to j minus or plus 1, which is m minus or plus 1. Then the argument of the coefficient here becomes m minus or plus 1 times L plus m omega plus m capital omega minus m in CT. If I take a time derivative of that, I get m minus or plus 1 times n minus m n sub c. You're going to get a resonance, which implies abnormally strong effects. If the mean motion of the planet you're interested in is m over m minus or plus 1 times the mean motion of the companion. The difference between the plus and the minus, if you have the minus, it's clear that n is bigger than n sub c, so the satellite is exterior. If you have the plus, the perturbing satellite is interior. I've assumed that it's exterior. You can carry this through just as well in the other case, but for simplicity, again, only look at the case n(c) over n minus 1. So that says that the ratio of the mean motions n over nc can be 2, 3/2, 4/3, 5/4, etc. You might normally say, well, we know that high Fourier harmonics typically have lower power than low Fourier harmonics, so these should get weaker and weaker. But because this ratio is getting closer and closer to unity, the objects are getting closer and closer, so that in fact the high M ones resonances are typically a little stronger than the low M ones. This already tells you something useful and interesting. It says that resonances of the form m over n minus 1 are going to be stronger than ones of the form m over n minus 2, because those are going to go like e squared rather than e. So you've already learned that not all ratios of small integers are equal, but the most important ones are the ones of this form, and anything with a higher number in here is going to be weaker. But you can do more. If we're interested in the behavior close to the resonance, it makes sense to look at what happens with the Hamiltonian when you only have the strongest resonant term in the Hamiltonian. So the total Hamiltonian, including the Kepler part, is minus gm squared over 2L squared. We've already agreed that the strongest term is the one that satisfies this condition. So it must depend on the square root of L minus G. There's some constant coefficient in front. And the cosine term is m minus 1 times the mean anomaly plus m omega plus capital omega minus m nc times t. Well, this is a big step forward. All you have to do is to solve the equations of motion in this Hamiltonian. But you can do better with our old friend, the canonical transformation. I'm going to make the canonical transformation to new variables, new momenta. One of them I'll call J sub s, and I'll make this m minus 1 L plus m omega plus omega minus m nct. Second one I'll call JF1. And then another one I'll call JF2. The new angles, for example, the one corresponding to this momentum is given by the derivative of the generating function with respect to the new momentum. So it's minus m minus 1L plus m omega plus capital omega minus m in CT. You can write down similar expressions for the other two coordinates, but I won't bother because we won't need them. And then, for example, the old momentum is the derivative of s with respect to L. So it's 1 minus m js plus jf1 plus jf2. I can go through this exercise for the other two old momenta and then do a simple algebraic elimination. And then to rewrite the Hamiltonian in terms of the new coordinates and momentum. When you do that, you have to remember that in contrast to the other canonical transformations we've been talking about, this one depends on time. And when there's a canonical transformation that depends on time, the new Hamiltonian includes a term which is partial of the generating function with respect to time. So you can go through this. It's easy to do to save a little time. I'll just write down the result. The Kepler component now looks like minus gm squared over 2, 1 minus m js plus jf1 plus jf2 squared plus a times the square root js times the cosine of theta s plus m nc js. Okay, what have we gained from this? The Hamiltonian's independent of the other two angles. So that means that these two momenta are constants of the motion. Since these are constants, the Hamiltonian only depends on one momentum, that is Js, and one angle, theta s. The reason for this notation of S and F is that theta s is the resonant variable, so it varies slowly, so S stands for slow. The other angles depend on the mean anomaly, which is non-resonant and varies rapidly, so the F stands for fast. So what we've basically done is gotten rid of the dependence. We've changed the momenta so that there are fast ones and slow ones. The fast ones are now constant, that is their adiabatic invariance, and all we care about is the slow one. You can do a little better. If you work out the expressions for the other two coefficients, jf1 is g minus h, jf2 is h plus m, all minus g. We assumed the inclination was 0, so g is equal to h, so jf1 is 0. Since the inclination, we would assume that the eccentricity is small, so this is small. This is basically the same as g, so this is fairly large. On the other hand, Js, since it's L minus g, is also small. So we've got one big momentum, one with 0, one that's small, and you can simply do a Taylor expansion of this. Notationally, I'll just call this square root of gm a0, so that I'm working with the second major axis instead of action. And when I do that, this Hamiltonian simplifies to Js times something I'll call delta minus 3 halves n minus 1 over a naught squared js squared plus a square root of js cos beta s. And delta is m times the mean motion of the companion minus m minus 1 and 0, this is square root of gm over a0 cubed. Okay, so where does this leave us? Delta is just the distance away from resonance. That is, this action, this momentum is a constant. It defines a semi-major axis, and that that means the difference between the mean motion of the companion multiplied by m and this characteristic semi-major axis is a parameterization of the distance away from resonance. This is the quadratic term that came from the Taylor series expansion, and so we have a Hamiltonian that depends linearly and quadratically with this funny dependence on the cosine of the angle. If I were to reparameterize the time and maybe reparameterize the actions, you could show that this would be equivalent to understanding the motion of that Hamiltonian would be equivalent to understanding the motion in the simplest possible Hamiltonian looking like this. What that says is that for all values of m, low eccentricity satellites in resonance can always be described, or at least can always be completely understood if you understand the motion in a Hamiltonian like this that only has 1 degree of freedom. You can understand, because there's only 1 degree of freedom and the Hamiltonian is conserved, you just have to plot the level surfaces of this Hamiltonian. This is sometimes called the second fundamental model for resonance. The obvious question is, what's the first fundamental model for resonance? And the answer is H is half JS minus delta squared plus cos beta s. That is without the square root here. This, of course, is the simple pendulum. And one of the conclusions is that because of the peculiar properties of orbits that are close to circular, this model with the square root in here is actually more relevant for celestial mechanics than the simple pendulum. It is, however, true that if you have orbits that are pretty eccentric with small perturbations, this varies only a little bit. It looks roughly constant when you're back to the Hamiltonian. Okay, I know we're slightly over time. I'll show one slide to illustrate the kind of information you can derive from this sort of treatment, which is it tells you about the capture of planets in the resonances when they migrate. If you migrate, you've got some external force which, say, is changing the mean motion of the companion or changing your mean motion, and therefore changing delta. There are two kinds of migration. Convergent, which says that the ratio of the mean motions is going towards unity, and divergent, which says that n over ns is, I don't know, going away from unity. So, for example, if you have an inner planet and an outer planet, and the outer one is moving in, that's convergent. Convergent in this case, where the perturber is exterior, corresponds to this mean motion increasing. So in our case, a convergent migration is delta from the final ingredient that you need to understand resonant capture is to recognize that if this is a slow process, you conserve the adiabatic invariance or the actions in the Hamiltonian, and the action is the integral of Js and theta s, that is the area inside the closed curve corresponding to a particular trajectory. Okay, so I've said that you can understand the motion just by plotting the level surfaces for this Hamiltonian. I can show you a plot of those surfaces. This is the same Hamiltonian. These are level surfaces as a function of delta. We were talking about convergent migration, so let's start, delta is increasing, start with negative delta. If delta is sufficiently large, the level surfaces just look like circles centered on zero eccentricity. This, I guess I should say, is a Cartesian plot in which the angle is WS. So if you have a nearly circular orbit a long way from resonance, it's basically near this point, maybe if there's a little bit of eccentricity, it's in a small circle going around this point. We now have migration, which starts to increase the value of delta, so you go through this sequence, and you can see that as you go through this sequence, the eccentricity grows. You stay close to this point, no matter how big delta gets. The area inside the closed curve is an adiabatic invariant, so if you've got a small oscillation around this point, as you migrate closer and closer to resonance, you still stay in a small circle around this point, but your mean eccentricity grows, that is, your distance away from the origin grows, and your semi-major axis stays at the semi-major axis associated with the resonance. If, on the other hand, you have divergent migration, you start a long way away at this point, and as the migration continues, this point eventually reaches a separatrix. Adiabatic invariant keeps you close to this point until you reach the separatrix, and then you pop out of this zone into this one. At that point, this is the area that has to be conserved, and so you eventually end up in an orbit like this. That is, you haven't been trapped in the resonance, but as you pass through the resonance, your eccentricity is excited. Okay, I don't, this is a lot of content. I don't expect you to go away from this with a complete understanding of how mean motion resonances work in planetary systems. But I would like you to go away with the feeling that, first of all, with a little bit of work, you could reproduce, you know how to reproduce these arguments, and that doing perturbation theory in terms of the 1A elements or other action angle variables is an extremely powerful tool for understanding a lot of phenomena that are both observationally relevant and almost impossible to understand as cleanly in any other way. Okay, stop there.